The topic of today is the testing of microphones with the FX100 audio analyzer. Please let me first introduce myself. My name is Markus Becker. I'm the technical director here at NTI Audio, and sitting next to me is Greg Schmiedle, our product manager. He will assist me mainly by also answering your questions during the webinar. We have prepared a couple of topics for today, starting with the scope of this webinar, followed by some information on the key challenges that you have to solve when you set up a microphone test and what is behind these major challenges. Some words about sensitivity measurements will be followed by a practical presentation, which is actually the major part of today's webinar. Coming towards the end, we will list some accessories and options that may be helpful for your application, which are available from NTI Audio. And at the end, we will provide some auxiliary information and at latest come back to the questions that you have asked during the webinar. The presentation will approximately last 30 minutes. First, we are going to restrict this presentation only to the acoustic microphone testing. There are also electrostatic couplers available on the market for microphone testing. These are not the topic of today. We are focusing only on testing and measuring the performance of microphones acoustically. Typical measurements are, of course, sensitivity, which is a key parameter, but frequency response and signal-to-noise ratio are also important, like distortions, polarity, maybe some other measurements in your application, but these are the most typical ones for microphone testing. Coming to the key challenges, there are actually two of them. First of all, the calibration of the test setup, which is always challenging in an acoustical environment, and followed by the environmental impacts and the elimination of these impacts. These are the two key challenges we are going to face, and we have to find solutions for them. And I will actually now dig deeper into these two topics and show them, to explain them to you and provide some solutions. Let's start with the test setup calibration. Calibration means that we want to make sure that our measurements are accurate, that we are really acquiring the correct measurement values. So the challenge comes from the fact that the device under test, the microphone we want to test, must be exposed to a sound source, to a reference loudspeaker that generates the test signal. And as you know, every loudspeaker has a nonlinear frequency response. It's of course the target of the manufacturer to get that frequency response as flat as possible, but there are always some roll-offs and some areas where it's not absolutely linear, and this of course compromises or may compromise the result of our measurement, because we are, for instance, looking for a perfectly flat frequency response in our microphone, so we should also have a similar behavior in the reference speaker. So the challenge is, how can we compensate this nonlinear behavior of the reference loudspeaker? And the answer is that in any case, we need a high precision reference microphone. High precision means it must have a perfectly flat linear frequency response in the bandwidth we are looking for, and it must have a known sensitivity. And if we have such a reference microphone, we can use it in two different ways. Either we compare the measured result from this reference microphone to the one from the device under test, and in this way we evaluate the behavior of the device under test. Or the second approach would be, we use the reference microphone to equalize the loudspeaker, to linearize the frequency response of our reference loudspeaker. Let's start with the first approach. We call it the indirect speaker compensation. In this schematic sketch, you see the elements that are required for this setup. We have the FX100 audio analyzer, which generates a test signal. We are actually using the glide sweep, which is a very well-known, very proven test signal. It's very fast, it covers a bandwidth of interest, and it has many advantages. So we generate this test signal from the FX100, amplify it, and bring it to the reference loudspeaker. Then we have our reference microphone, which is indicated here, plus, of course, the device under test, the microphone we want to evaluate. All of that in a room. So the test signal we generate has a flat level, a constant level over the frequency. However, when we look at the acoustical frequency response that has been generated from the loudspeaker, it is not linear, it is shaped, as you can see here in the schematic graph. So we measure this actual behavior of the loudspeaker. You see that in the changed color. It's now the green color indicating this is the measurement result from our reference microphone. And then we can compare this curve with the response from the device under test. This is the blue curve here, so we have the green dotted curve from the reference microphone and the blue solid curve from the device under test. And by comparing these two curves, actually by measuring the difference between these two curves, we get the frequency response from the device under test. Due to the fact that the reference microphone has a linear frequency response, we are sure now that we have here the actual frequency response from the device under test, the microphone we want to evaluate, and this way we have excluded the impact of the reference loudspeaker. The second approach, the speaker equalization, is based on the same test setup as you can see here. Again, we are starting with a glide sweep test signal with constant level, and we are measuring the actual frequency response from the loudspeaker with our reference microphone. But now we are using this measurement result to apply a weighting on the test signal. We invert this shape and use it as weighting for our test signal. And the consequence of this is, in an ideal case, that the acoustical frequency response from the reference speaker now is flat, is absolutely linear. This looks simpler as it is. Keep in mind, this is a bit of demanding procedure, but it is feasible if you have high quality devices in your setup. And now we can, of course, directly measure the frequency response from our microphone here, the one we want to test, and we get the same response as in the setup before, but now we get it directly with a direct measurement due to this linearized, equalized frequency response from the reference speaker. Once again, keep in mind, this is the more demanding approach. It requires high-end components, high-end reference speaker, and a thought-out calibration routine to get to this point where we have linearized the frequency response. Some words about microphone sensitivity. Up on top here you see the formula, the definition formula for the sensitivity expressed in millivolt per Pascal. We have to measure the voltage that comes out of our device under test and divide it by a reference sound pressure level multiplied by 20 micropascal. This is the definition for microphone sensitivity. So if we want to evaluate this value, we need the voltage and the sound pressure level. The sound pressure level, for instance, at 1 kilohertz, and that is actually acquired with the reference microphone, because here we know the sensitivity, and by measuring the voltage from the reference microphone, we can calculate the corresponding sound pressure level exactly. And the voltage from the device under test is directly measured by the FX100. Keep in mind, when you plot the sensitivity over the frequency, let's say 100 Hertz to 20 kilohertz as here. Keep in mind that this curve always refers to this reference point. This reference point is given by this reference sound pressure level. In our case, that would be at 1 kilohertz. The other major challenge that you may encounter in your concrete test setup is room reflections, the impact of the environment. In this sketch you see that the sound coming from the reference speaker, the direct sounds, hits the microphone we want to measure. But in reality we always have to face room reflections, reflections from the ceiling for instance, or reflections from the wall behind or another surface, hard surface in the room. So these reflections will overlay the direct sound at a certain point, and that has of course an impact on the recorded signal, on the acoustical signal at this microphone capsule here, and that compromises, somehow falsifies the measured frequency response, for instance, of the tested microphone. So the room reflections are a superposition to the direct sound, and that is something we do not want. We have to find ways how to eliminate that. One way would of course be to shield the walls and the ceilings in the room, to go into an anechoic chamber, but this is a very expensive way, a very complex way, and it's not really applicable for mass production, for instance. So we have to find another solution, and I'm going to present one to you in a few minutes. Well, we are actually at that point, at the practical presentation, where I'm going to show you these different solutions. My demo setup here includes exactly the components I have shown you in the graph before, the FX100 plus an amplifier. We are using a high-end reference loudspeaker with a M2010 reference microphone. We have a dynamic voice microphone as device under test. And I'm going to show you two different software packages. First, the FX Control software that comes along free of charge with every FX100 analyzer. This software is a very flexible, very powerful solution for lab applications, but it can also be used in smaller production sites with, where we are not talking about very high volumes. The second software here, the Artemic FX, has been specifically designed for production testing. It has a straightforward, very intuitive operation, but of course it's more restricted to microphone testing compared to the FX Control. Just one first short look here at the wiring. This is a feature of the FX Control software where you can symbolize the test setup. We have the FX100 analyzer, we have the reference speaker and the two microphones. Here the reference microphone and the voice microphone we want to test. Both are connected directly to the FX100 analyzer. So the first step we have to execute is the calibration of the reference sound pressure level. You remember from the sensitivity measurement, we need a defined sound pressure level at the microphone. Actually, we are talking now of the reference microphone. We want to make sure that there is a specified sound pressure level. And for this purpose, we have activated here what we call a regulator. This is a module which is included in the software, and this module automatically evaluates the required output level, generator level of the FX100, so that the input signal, in this case the input signal from the reference microphone, corresponds to this 90 dB SPL. This is an automated routine. I just have to click on the run button. And you see here the result is we need 0.8 dB volt to achieve these 90 dB SPL. So I'm going to apply this level and swap to the next window. And now I'm going to present you the solution how we can exclude the room reflections I have mentioned before. And for this purpose we have a very nice assistant. This is this window. In here I'm gonna just run one cycle. So you have heard the glide sweep test signal. You see up here the energy time curve of the incoming signal, and down here we see the frequency response that has been acquired from the reference microphone. Just adjust the scaling of that graph. You see a lot of ripple in this frequency response, and this ripple is of course not coming from the microphone. This is the impact of these room reflections. The overlay of these room reflections to the direct sound causes this ripple. And we see that also here in the energy time curve. Alternatively, I could also show you the impulse response. This is just a different way of displaying this incoming signal. And here we see also these reflections. This is a direct sound from the speaker to the microphone, and these are the room reflections. So by adjusting this time window here in front of these reflections, I can eliminate directly the impact of these reflections. So what you see down here is not a kind of smoothing. This is actually a procedure that makes sure that these reflections are not considered for the measurement. And how does that work? This line that I moved up here, this is a time window, which means that all the parts of the signal, you see here, this is the time axis, all the parts of the incoming signal behind this line are not considered for the measurement. I'm only considering the signal from the direct sound when it hits the membrane of my reference microphone to this point here. And everything behind, all the reflections are just filtered out, are just eliminated in this way. Maybe you have noticed here there is a black vertical line which has appeared, and that is an artifact that is a consequence of my time windowing. Because I'm restricted to this limited time here from the direct sound to this start of this time window, I cannot represent the very low frequencies in my frequency response. I can show you the impact a little bit more if I move that further forward here, I further shorten this time, and then you see this line comes further here to the right hand side, which means that this part here to the left, the shaded part of the curve, it's just an estimate. It's not an exactly, accurately calculated measurement result, because we are missing enough samples to really do that exactly. So going back here to the, what was it, about 7 milliseconds. This is the part which is an estimate, and this part is accurately measured by the system. So I confirm my setting and switch to the measurement result. We see here the 90 dB SPL, that was our reference sound pressure level as we have adjusted it in our first step. We see here down the voltage from the reference microphone at 1 kHz and the calculated sensitivity of the microphone expressed in dB volt per Pascal and down here in millivolt per Pascal. And here on the right hand side we see the green curve. That was our reference microphone. Actually the curve that you see here represents the behavior of the reference loudspeaker, because the reference microphone itself would have a flat frequency response. And down here we see the recorded measurement result from our device under test. And by comparing these two curves, by calculating the difference, we get the actual frequency response of our microphone of the device under test without the impact from the reference loudspeaker, without the characteristic of the reference loudspeaker. So this is the pure behavior of the measured microphone, what you see here on this graph. This is what we are looking for. So let's switch over to the other solution, to the equalization of the reference loudspeaker. And for this purpose, I'm using this software. It is important to know that both solutions, the indirect compensation and the speaker equalization, both can be implemented on these two software packages. It's not that only one software can handle one of these solutions. They are all support both solutions. We just, for simplicity, decided to present the indirect compensation with the FX control software and the loudspeaker equalization with this Artimic FX software. So I have here my project with the test parameters. The test parameters are of course all editable. for instance, the measurements I want to execute, the glide sweep parameters, the bandwidth of the glide sweep, or down here the tolerance limits, which is the headroom of my acceptance range. I can adjust here manually or numerically the way I want, and so on, here in the edit section. Next step would be to calibrate the setup. And the calibration means now this is the equalization. And the equalization or the calibration actually starts with the time window setting. So you see a similar picture as before. We have here the impulse response, down here the ETC, the energy time curve of the incoming signal. I activate now my time window and adjust it to the same value as I have evaluated before, these 7 milliseconds. And now I start the calibration, and I will be silent for a couple of seconds so that you can listen to this procedure. It's an iterative procedure which is necessary to really come to the point where the frequency response of my reference speaker has been perfectly linearized and equalized. So the calibration procedure is finished. You see that down here by this green bar. We see up here the linearized frequency response of the reference speaker, and here the weighting that had to be applied to get to the point where this frequency response is here flat. Keep in mind that the calibration needs to be executed, let's say, once per month or maybe once per week, depending on the stability of your test setup. Next step is the acquisition of reference curves. When we want to verify the behavior of microphones in a production, we need, of course, a reference database, and this reference database is acquired by measuring good working microphones of the type we want to test. You see here the frequency response of my reference, of the microphone I'm using as database. You remember this is the same shape as I have acquired with the other software. This is the same frequency response. Down here we have the distortion result, the polarity, and the signal noise ratio. I'm just repeating this measurement a few couples of times. You see very stable results, always the same curves coming in here, very, very small fluctuations. So we have a pretty stable reference database. We can exit this mode and directly go into the production mode. And this is the one where we are now testing the microphones. You see here the green bands. This is our tolerance band, so all the tested microphones must be within these bands to be passed, or here within these numerical values. So this is the mode you would apply when you do production testing. Let's get back to our presentation. Summarizing what we have just seen, we have started with the indirect compensation by using the FX control software, followed by the speaker equalization solution with the Artemic FX software. So these two methods, the indirect compensation and the speaker equalization, have of course their pros and cons. The indirect compensation has the advantage that it's pretty simple to implement, it's a very robust solution. The drawback is that if you want to acquire the sensitivity of your microphone over the frequency range, you have to cope the fact that the sound pressure level, which is generated and coming to this microphone at different frequencies, may vary. So the sensitivity measurement is not acquired in a situation where the sound pressure level is almost identical regardless of the frequency. And this challenge actually would be solved by this second approach because we have linearized our reference speaker. However, the drawback of this solution is here that we really need to use very high-end devices, and we do have a demanding procedure to calibrate the device. Of course, the software can help you, does assist you in this process, but still it's a demanding procedure and not to be underestimated. Coming to the accessories and options that NTI Audio is offering for your application, one we have already mentioned before would be our measuring microphones like the M2010 that we have used in our test setup here. If you're looking for digital MEMS microphone testing, maybe even on the chip, then you can use our MEMS mic test box with 8 channels, and that is just simplifying the connection and the quick testing of these MEMS microphones when they are still on this chip. Another auxiliary device could be an ampermeter that can be connected to the software. It's supported, and this allows you to verify, to measure the current consumption of the microphone under test. And last but not least, if you want to acquire polar plots from your microphone, you can use a turntable. This is also, we have built in the interface to this device in our software, so you can connect it to the Artemic FX software to acquire polar plots. Well, we are at the end of our presentation. Now let me look at the questions that have come in. Yeah, I see one question regarding the software licenses. As mentioned before, the FX Control software is free of charge, does not require any license. It comes along with every FX100 analyzer. The other software, the Artemic FX, must be licensed, whereby the license is installed on the FX100 instrument, which means that you can install the software on several computers. It's not copy protected in this way, and you can run or you can control the FX100 analyzer from any of these computers. A second question regarding the reference microphone, whether the system would also support reference microphones from other manufacturers. The answer is yes. If you already have a high precision microphone class 1, then you can of course use that and connect it to the system for your application. The FX100 has a built-in phantom power supply and ICP power supply, so it should be possible to directly connect the microphone to the instrument without the need of an external power supply. Another question here refers to the polar plots. I want to show you that briefly. I haven't a polar plot installed in my setup here, but I can show you briefly how this would work. I would create a new project. I'm going to call that polar plot here. I select the corresponding project type here, and by creating this project, I can immediately enter the corresponding test parameters, again the test signal parameters, the glide sweep, start, stop frequency, and so on. But here also I have the possibility to edit the number of steps for my polar plot, or the rotation direction of my turntable, and so on and so forth. The frequency at which it is will be acquired. So this functionality is included in the software. Yes, there's another question, and this is regarding the data export or reporting, actually, the reporting of acquired measurement results. I show you that also in this example. This feature, by the way, is supported of both software packages, also of the FX Control. So you have the possibility to export your data in two different ways. You can do number one, which we call data logging. This is an export of raw numerical data, plus, if you like, screenshots from the graphs. And these raw data are saved in a file, in a formatted file, which then can be imported, for instance, into Microsoft Excel. So you determine the target folder, and the system will automatically write these results into this file. The second solution would be the reporting, and here you can set up a template, a Word template or a Microsoft Excel template, and then these data will automatically create a document that has been layouted according to your demands, and this way you can create report documents directly from your measurement. This procedure is a little bit more demanding. It's described in the help files, and of course we will always be happy to assist you if you want to implement that. Okay, I don't see any more questions. Nevertheless, if you have any open issue which comes into your mind, please don't hesitate and contact any of our partners worldwide. We will be happy to assist you. I'm going to close this webinar now. Thank you very much for your interest. Thank you very much for joining us. Hope to see you again in a future webinar, and wishing you a brilliant Easter weekend. Thank you and bye-bye.